Hey everyone, welcome back to another PattysLab video. It's been a while since my last upload, but this took much longer than I had anticipated. So lately I've been watching a couple of videos of people that make clear ice. And I wanted to try this out for myself, but of course I wanted to step it up a notch and create a mold that could be 3D printed and used to make a clear ice diamond. And I think it turned out pretty good. And in this video I will show you the concept behind the mold, my failed attempts, the improvements, and also the slicing of the 3D printed parts. Let's get started. Here you can see a cross-section of the final mold. And this design was achieved after many iterations. I will now show you these iterations and after that jump back to this model and explain the features that made it successful. This first attempt had a far too little air trap and therefore did not make the ice clear. Also, since this was a single part insulated mold, the ice was super hard to remove. Therefore the next iteration was a two-part mold and would make it far easier to remove the ice by just letting warm water flow over the sides of the insert. The air trap was also much bigger, but the problem with this version was that the bottom was not insulated. So, logically, the next iteration would be a mold that would have an insulated bottom, that still could be printed on an FDM printer and also be watertight. That's why this kind of cone shape was used. It took some tuning to print this part watertight and with a decent quality, but I will explain that later in the slicer. This part also had a diamond insert which could be removed in theory. This insert would evolve into several versions, but two big problems remained. One, getting the insert out of the insulated cup, because if everything is frozen and expanded, the removal is really hard. And two, is getting the ice diamond out of the one-part insert. So this first problem was solved by adding a hole into the insulated cup that could be filled with warm water. And the second problem was solved by changing the one-part insert into a split insert that could be opened up, and in this way the diamond could be removed. I will now jump back to the cross-section of the mold and show you how these features are implemented. So we have 4 cutouts in these 4 locations, and these cutouts house 2 O-rings to keep the inner mold together. But actually the inner mold is moved up a little bit, and therefore the top O-ring is resting on top of the insulated cup. And this creates a little bit more space here, as you can see in the bottom, for water to go. Then this hole on the side will be covered up, and the air between the walls ideally should be stationary and therefore conduct less heat. Then the mold could be filled up with water all the way up to this edge, so the entire inner section will be filled with water. Then ideally the heat should only escape from the top, and in this way it's freezing the water from top down all the way to the bottom, and on its way it's pushing the air downwards in the lower section of the cup, which still should be liquid. Then when all the water has frozen, the diamond should ideally be clear, and this ice should contain all the air. Then some lukewarm water could be poured in from the hole, filling up the insulation layer, and then this is melting some ice around the perimeter of the inner layer. And therefore, in combination with these 3-degree tapered walls, could the inner mold be pulled out fairly easily and hopefully containing a clear ice diamond. So now it's time to pack the ice mold and put it into the freezer. So we have a 3D printed insulation cup, we have an insulation sleeve made of floor insulation, a small cup to pour water into the mold, we have the split diamond shaped mold, also 3D printed, we have 2 O-rings and a roll of tape. So we need to cover up the hole into the insulation cup, and this is to make sure that the air in the insulation cup will be remaining stationary. Now it's time to add the 2 O-rings to keep the diamond split mold together, and I will include the dimensions of the O-rings in the description so you can order them for yourself. Now it's a smart idea to put the insulation cup into the insulation sleeve before you're gonna add the water and everything to prevent the spillage. And after that, you can just place the inner mold inside of the insulation cup. It's now time to fill up the mold with water. So it's smart to use mineral water if your tap water is full of calcium or, for example, contains a tasteable amount of chlorine that some countries have in order to decontaminate their water. It's now time to pour in the last bit of water and fill the mold up to the level that was shown in the drawing. Then before the mold is put into the freezer, it's smart to gently tap the sides to get rid of any air bubbles. Now it's actually time to place the mold into the freezer. As you could see, I made some kind of improvised stand that would allow the mold to be positioned into the center of the freezer's drawer. Also, note here that I used the bottom drawer since I thought that it would be best to not have a cooling plate below the mold. I set the freezer to its lowest setting, and that corresponded to a temperature of -10 degrees Celsius, and I measured it with a thermocouple. So it has been around 24 hours now, and it's time to take the mold out of the freezer. And the important thing to note is that actually the inner part of the mold has been pushed out quite far out of the insulation cup, and this is due to the expanding nature of ice. So the insulation cup can be moved out, then the tape can be removed, exposing the hole. Then you can warm up the tap a little bit.
One eternity later.
And now we can see that the air has been trapped here in the bottom, and then hopefully the ice diamond will be clear. So I'm gonna use a knife now in order to get rid of this ice. So now I'm gonna use a dentist pick in order to remove the O-rings. So now it's time to gently open up the mold by wiggling it back and forth until one of these sides pops loose. So now the only remaining task is to remove the slippery ice diamond from the other part of the mold. And it was this moment that I realized I fucked up. So pretend that never happened. Luckily the diamond is still in one piece and we can still continue. As we can see, the diamond turned out to be pretty clear, but there is still a little bit of air left in the bottom. So I think by making the compartment that houses the water inside of the insulation cup a little bit larger, we can get rid of this air entirely. So this can easily be done by scaling the insulation cup in the Z direction. Speaking of scaling the insulated cup in the Z direction, this is the last part of the video, the slicer settings. But before we move into the slicer settings, I have to mention this. Before people will comment about their concerns regarding the food safety, I will write a small section about this topic in the description, because you might actually want to use this for a fancy drink. Furthermore, I will not only upload the STL files, but also the step files in case you want to improve on this design. For the slicer settings, I will only cover the insulated cup, since this part needs to be printed watertight. And this can be achieved by using large diameter nozzle. I used a 0.8mm nozzle, or you can set your line width to 0.8mm. A standard 0.4mm nozzle will then over extrude to create a 0.8mm line of plastic. In combination to this, I used a fairly coarse layer height of 0.3mm. If there are less layers, there's also less likely that a leak will occur. Temperature during this print is set to 220 degrees Celsius for PLA. I created the mold in such a way that it uses 2 times a 0.8mm line to create the walls. You can experiment with increasing your normal flow rate by 1 to 5%. So let's say from 100 to 105 or 100 to 102. So you might have noticed that my insulation cup was actually covered up with epoxy. And the reason for this is that I didn't slow down the print from this point on. And before this point, basically the printer, the hotend, is moving over the inner part and then moving to the outer part, and this will create enough time for everything to cool down. But from this point on, the printer will only print the outer perimeters, and with such temperatures and feed rates, your edges of this border will basically become very saggy. So what I did in order to fix this is I set the minimum layer time from 5 to 20 seconds. And this is ensuring that the hotend will spend at least this amount of seconds onto a single layer. If you made it this far, you are the best. It took a long time to make this video, so if you liked it, please leave a thumbs up and hit that subscribe button. And I hope to see your even better ice diamond, or perhaps some other fancy shape. Thanks for watching, and remember, just try to DIY.